All right, so number 17. Says, find an expression for the area under the graph of f as a limit. Do not evaluate the limit. So we have f of x is 2x over x squared plus 1. So, and we're going from 1 to 3. So just as a reminder, what they're looking for is the limit as n approaches infinity of I goes from 1 to n, and we have our f of x sub I times delta x. And that is a wonderful sigma. If you can draw one like that, I think I should give you extra credit. So our delta x is always going to be our upper limit minus our lower limit divided by n. In this case, we don't know what n is. Excuse me. So delta x is going to be 2 over n. The value we're going to plug in for x, our x sub i's, if we're, this was always kind of a right endpoint approximation. So if we think about this graph, and I'm just going to draw a graph in general, it's not the actual graph, although I suppose I could. 2 over 2, 6 over 10, that's going to be down here somewhere. I don't know, maybe like that. So for right-hand endpoints, if this is my first, my x sub 1, I know that it starts at 1, and the distance between them is our delta x. So our x sub i's are going to be 1 plus 2 over n times I. So each time we move across, we get a new, we get 2 over n added to our x value. So then our approximation becomes the limit as n approaches infinity I goes from 1 to n. This is going to be 1 plus 2n, 2 over n times I times 2 over n. And then I can finally, my last step will be plugging in this 1 plus 2 over n times I into my original function. So it's still going to be the limit as n approaches infinity of 2 times 1 plus 2 over n times I over 1 plus 2 over n times I squared plus 1. There's my function. And that whole thing is multiplied by 2 over n. And I would just leave it like that. You don't need to multiply out the denominator. You don't need to distribute the 2. You don't need to combine any terms. That would be fine. And one thing I forgot is my summation. There we go. Let me rewrite it. Limit as n approaches infinity of the sum. I goes from 1 to n of that whole thing. And that's an I there. All right. All right. So any other questions on either 5.1 or 5.2? So 5.1 and 5.2, we used ways to estimate to find integrals or area between the x-axis and a curve. Today, I know it's going to disappoint you. We're going to look at the shorter way to do it rather than using rectangles and finding where we're measuring our heights from. So we're going to evaluate definite integrals today. All right. So there is a theorem called the evaluation theorem. It says if little f is continuous on the interval from a to b, so again, big thing with integrals, we want a continuous function. We will actually take a look at what happens if it's not continuous at the end of the chapter. Then the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F is called the antiderivative of little f, which just is a fancy way of saying that if I take capital F and take its derivative, I get little f. So this is going to be working backward on derivatives. So a lot of times people will, when they, at least at starting, when they take integrals, they'll look at the function and say, okay, what function is that the integral of? And kind of work backward that way. So a couple other ways that you could see this written. The way it was written on the previous page is the most common. I actually use this after I've taken the integral, just to show that I'm evaluating it. So that's kind of this method or that notation. All right, so here it is. Evaluate the integral from 1 to 3 of e to the x dx. So what function, when I take its derivative, gives me e to the x?
E to the x.
Yeah, so we're just going to get e to the x, and we're going to evaluate it from 1 to 3. So that's, again, that's one way that you'll see me write it, which just means take 3 and plug it in, minus what we get when we plug in 1. And we don't need to estimate if you don't want to. This would probably be like maybe a multiple choice on the non-calculator section of the AP exam, something like this. And so they would leave it in terms of E rather than finding the decimal approximation. You certainly can find the decimal approximation, you just don't have to. Okay. So what we had just done is called a definite integral. We could also get something called an indefinite integral. So for a definite integral, we have limits on our integral, and it represents a number. We get a value as our answer. An indefinite integral does not have limits, does not have values on the integral symbol. So what our answer would be is a function. And in our old book, it was on page 375. In the new book, it's on page 358. Let me see if I can write that a little bit better. But there's a list of indefinite integrals. There are, I don't know, about a dozen, 14, I guess. And they're just things that you're going to have to memorize. Just like we memorized the derivative of the trig functions, just like we memorized what the derivative of e to the x was. Same thing with these indefinite integrals. So a problem might ask you find the general indefinite integral that might not even have the word general there. It just might say find the indefinite integral. So I have the integral of 10x to the fourth minus 2 secant squared x. And so, as I said, we're kind of working backward from derivatives. So when we had a power rule, we would bring the power down and take x to 1 less power. So we would multiply by the current power and then take x to 1 less. For integrals, we work backward. So, okay, the last thing we did to find a derivative was we subtracted 1 from the power. So we do the opposite. So we're going to add 1 to the power. So that's going to become x to the 5th. With derivatives, the first thing we did, we brought the power down and multiplied. So for an integral, sometimes called an antiderivative, we do the opposite. So we've got that power, we're going to divide by that power. And then what function had its derivative as secant squared? Tangent, yes, tangent. The last thing, if we have an indefinite integral, if we don't have values for limits on our integral, we are going to add a constant. And we're just going to call it C. In other words, let me simplify this and then I'll tell you the in other words. So this is 2x to the fifth minus 2 tangent x plus a constant. So what that means is if I took the derivative of this function, I would get this function. And it could be that what the constant does is it would just move the function up or down on the y-axis. Because we don't know what the original function was, we have to include that constant. If we had limits here, because we take the upper minus the lower, the constant in essence would get subtracted off. For the most part, there really isn't a quotient rule for integrals. There are ways that you can deal with quotients. I'm going to show you one way if the quotient is just a single term. So evaluate the integral from 1 to 9 of 2t squared plus t to the 5 halves minus 1 all over t squared dt. What I would do is actually divide each term by t squared. So we'd have 2t squared over t squared plus t to the 5 halves over t squared. Oops. Minus 1 over t squared. Simplifying, that would be 2. If I subtract, that would give me t to the 1/2. And 1 over t squared is the same as t to the -2nd. Now I can take the integral. The integral of 2. Let's see, if I think of what function when I take its derivative gives me 2, that would be 2 times my variable. if I have the power rule like I have here, I am going to take the variable to one more power, and then I'm going to divide by that power. Well, dividing by 3/2 is the same as multiplying the whole thing by 2/3. So a lot of times we'll just talk about multiplying by the reciprocal if it's a fraction. Add 1 to my power here, I get t to the negative first. Dividing by -1 just changes the sign. Evaluate that from 1 to 9. Plug in 9, plug in 1. This would be 18. The square root of 9 is 3. 3 cubed is 27. 27 times 2/3 is 18. Again, you could certainly use a calculator to simplify this, although don't get too reliant on the calculator because it will only be available during part of the AP exam. So this is 36 1/9 minus 3 2/3. That would be 4/9. No, that would be 6/9. So this would be 4/9. See if I did that right. So if I borrow 1, let's see, 36 1/9 minus 3 2/3. Well, this would be 3 6/9. So I have to borrow 135 10/9. Yeah, okay, good. So like I say, you could simply plug the function into a calculator, look at the value at 9, look at the value at 1, and subtract. Questions? Okay, we're going to actually do another section, but this will be the first part of your assignment. And I should check, I think the page may be wrong. Of course, the page is wrong. I should have checked before I started class. So this is on page 363. The second part of what we're going to do is actually pretty short, as was this one, I think. So let's open that one up. All right. So still evaluating definite integrals. One of the big ideas of an integral is it tells us the net change. So if we take the integral of a rate of change, so if f prime of x is a rate of change, then the net change, the difference from where we started to where we ended, would be the integral from a to b of f prime of x dx, or capital F at b minus capital F at a. And that can be used when for any rate of change. It is not total change, it's just the net change. So think about, and we'll do an example in just a minute, but think about a particle that is moving. It might move to the right and then to the left and then back to the right. The total change would be taking into account when it changes direction. The net change, the difference from where it started to where it ended, would just be f of the ending position minus the starting position. So I'm going to actually just skip these examples. It's just more of basically, if you take this antiderivative or integral of this rate of change, it tells you this thing. So you're more likely to see an example like this. A particle moves along a line so that its velocity at time t is v of t is equal to t squared minus t minus 6, where we're measuring in meters per second. Find the displacement. This is another word for net change. Of the particle during the time period from 1 to 4. So velocity is just a rate of change for position. So the net change, the displacement, is the integral from 1 to 4 of the velocity function. So to evaluate, we take t to 1 more power, divide by that new power. T to 1 more power, divide by that power. And anytime we have a constant, it's going to get a t. And we will evaluate that from 1 to 4. So we get 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. Uh, 16 over 2, I think that's just 8. So one of the nice things here is if I look at just kind of piece by piece, 64 over 3 minus 1 over 3, that's 63 over 3, which is 21, minus 32. And this is minus negative 6.5, so that's going to be plus 6.5. Double checking my work here. Looks okay. Oh, yeah. All right, so we get 27.5 minus 32. It's negative 4.5. So in other words, the particle ended up 4.5 meters to the left, if you want to think of that, or below, if you're thinking of it moving up and down from where it started. If instead we want to find the total distance traveled, be similar to things we did when we were working with derivatives. We would want to find where the particle changes direction. And so, again, my velocity minus t minus 6, factoring, we would get minus 3 and plus 2. So t equals 3, t equals negative 2. That one's not on our interval. The 3 is. So if you think about that velocity function, it's a parabola. It's going to be negative between negative 2 and 3. And you can, again, you could justify that with a graph if you wanted. Because it's negative, we're going to take the integral from 1 to 3. Again, my answer there is going to be negative distance. So I'm going to take the opposite of that. plus the positive distance be the integral from 3 to 4. The integral is going to turn out the same as far as the function goes. And then, of course, we would plug values in and evaluate. And I guarantee I know what you're thinking. Mr. Gingrich, isn't there an easier way? Of course there is. So let me show you the easier way. So on the graphing calculator, and if you have a TI-84, you're going to absolutely love this. If you have an 83 plus, you can still do it. It's a little bit more difficult. What I would do is go to mode, excuse me, and make sure that math print is highlighted. That's going to be key. And if I go to the math menu, notice way down here, option 9, FN int. So you'll see I have an integral symbol. So my original interval went from 1 to 4. I want to make sure I'm taking just getting the overall distance traveled. So I could do the absolute value of my velocity function. And your calculator will calculate that. Again, don't rely too heavily on your calculator, but knowing these little shortcuts is helpful. So if I go back 10.167, I believe is what the calculator told me here. This is approximately 6.7 meters. All right, so the second part of your assignment is going to be dealing with rates of change and what those integrals would tell you. Pretty straightforward, I think. For number 70, they actually give you some data for the velocity of the space shuttle after it's launched. And so it says, use a graphing calculator to model these data by a third-degree polynomial. That basically means use cubic regression. So you'll enter the data into your calculator, and once you have it in your two lists, you will choose Stat, Calc, and option 6 is cubic regression. So you will want that for part A. And then for part B, it asks you to estimate the height 125 seconds after liftoff. Take the integral of what you found and evaluate it from 0 to 125. Questions? If not, have a great weekend, and we'll see you next week. I know it doesn't affect this class at all, but next week, because there's no class on Monday, the odd hours for cohort A will meet on Tuesday, even hours will meet on Wednesday, so there'll be no office hours next week. And then Thursday and Friday just remain the same. So I will see you guys next Friday, normal time for class.